Hi everyone, today we're going to talk about finding limits algebraically. So last week we talked about graphically how to do it. Now we're going to talk about algebraically. And here's the idea. You always, like we said before, we always want to try direct substitution first. However, that might not always work. So what would happen is if direct substitution gives you 0 over 0, right, which you can't have. And sometimes people think, well, but anything divided by itself is 1. That's true except when you have 0, because you can't have 0 in the denominator. So 0 over 0 is called the indeterminate form, okay? And you cannot determine the limit the way that it's written in that form. So that means that we have to figure out a different way to go ahead and evaluate the limit. And we do that using some different algebraic techniques. So the first one I want to show you is this first example, and we're going to actually use factoring to solve it. So let me show you what happens when we plug -1 in directly. If I do direct substitution with -1, I have 2 times -1 squared minus -1 minus 3 over -1 plus 1, which then gives me 2 plus 1 minus 3 over 0. That gives me 0 over 0. Okay, and we cannot have that form. So what I'm going to do is, instead of trying to do direct substitution to evaluate the limit, I'm going to go ahead and factor that. When I factor that numerator, that gives me 2x minus 3 times x plus 1 over x plus 1. So if you're in a situation where you have a polynomial over a binomial, try to factor it, right? And you obviously want to try and get the same, one of the factors to be the same as the one you have in the denominator, because then you can cancel those, and now you have a problem that's much simpler and a problem that you can just use direct substitution. Okay, so now I can just directly substitute into 2x minus 3, so that's going to give me 2 minus 1, 2 times -1 minus 3, which would give me then -5, and that would be my limit. Okay, so first you have to check direct substitution, and then if that doesn't work, then if you can factor, go ahead and factor. Okay, that allows you to cancel your common factors, which then allows you to find the limit. Okay, let's look at example number 2. If I go ahead and did direct substitution into this one, that would give me square root of 3 plus 1 minus 2 over 3 minus 3. And that's going to give me square root of 4 minus 2 over 0. So that's going to give me 0 over 0 as well. Now, with this one, there's nothing to factor, obviously. But as soon as you see that radical in there, whether it's in the numerator or in the denominator, what you want to do is you want to rationalize. And rationalize means multiplying by the conjugate. We've done this before. Back at the beginning of the year, you did this in Algebra 2 as well, okay? But we're going to rationalize. So rationalizing, we're rationalizing the numerator here. We are going to multiply by the conjugate. So the conjugate would be x plus 1 plus 2. Remember, the conjugate just changes the sign between them. And whatever I multiply the numerator by, I have to multiply the denominator by as well. Okay, and so when I do that, I end up with the limit as x approaches 3. Now, because they're conjugates, I can just multiply the first 2 terms together and multiply the last 2 terms together. So if I multiply square root of x plus 1 times square root of x plus 1, that gives me x plus 1. And then -2 times 2 would give me -4 over, and I'm going to leave this factored. I'm not going to distribute it, and you'll see why in a second. When I go ahead and do that, that leaves me with x minus 3 in the denominator, right? If I simplify that, that leaves me with x minus 3, and then I can cancel x minus 3 over x minus 3. And that leaves me with 1 over the square root of x plus 1 plus 2, and now I can go ahead and direct substitute. So I end up with 1 over square root of 3 plus 1 plus 2, which is going to give me 1 over 4. One other thing I didn't mention before, when you are going through the process of evaluating the limit, make sure that you carry this notation through the whole problem, right? Otherwise, it's technically wrong. So carry it all the way through until you go ahead and substitute the number in. Okay, that's also very, very important. Okay, so in this one we have a complex fraction. If I were to go ahead and just do direct substitution, I would end up with 1/4 minus 1/4 over 0, which gives me 0 over 0, which obviously I can't have. So if let me rewrite the problem here. What I want to do is I want to simplify my complex fraction. And if you remember back when we talked about simplifying complex fractions, we said take all of your denominators within the fraction itself. So we have x plus 4 times and 4. So that is going to be what I multiply every single term in the fraction by. So I'm going to multiply every term in the fraction by x times x plus 4. I'll multiply, oh sorry, not x, that's a 4. Sorry, multiply by 4 times x plus 4, multiply this by 4 times x plus 4, and multiply this by 4 times x plus 4. Okay, so I just found the common denominator within the complex fraction, and now I'm multiplying every term of the complex fraction by that. So what happens? My x plus 4's cancel there, and that gives me just 4 times 1, or 4. Here my 4's cancel, so that gives me negative 1 times x plus 4. And then in the bottom nothing cancels, so I have 4 times x plus 4. So if I go ahead and I distribute that negative, that gives me 4 minus x minus 4. And then the 4 and the minus 4 add to 0, so that leaves me with the limit as x goes to 0 of negative x over 4x times x plus 4. Now from here I can cancel these x's, right? So this is really just algebra from this point on. And actually all of this was just algebra too. And that leaves me with negative 1 over 4 times x plus 4. Well, now if I go ahead and substitute 0 in, I end up with negative 1 over 4 times 4, which gives me negative 1/16. Okay, so that would be my answer there. So we did factoring, we did rationalizing, and we did simplifying. In this last example, if I go ahead and plug 2 in here, if I go ahead and plug 2 in, that's going to give me 3 times 2 squared plus 5 times 2 minus 2 over 2 minus 2. Now that's not going to give me 0 over 0, that's going to give me 20 over 0. And in this case, as of right now, we don't have a way to solve this. We'll get to that. So we would just say that does not exist. Okay, it's not 0 over 0, it's a number over 0, and because you can't divide by 0, that does not exist. Okay, when we start talking about infinite limits, we'll get more into this and what's actually happening there. Okay, but for now, we'll just leave it as does not exist. Okay, let's go ahead and I explain that up here. It says that it's basically increasing or decreasing without bound, or it does not exist. So for now, we're just going to say it does not exist. Okay, but let's look at this next example. We're investigating this very special case, and just in the interest of time, I'm going to go ahead and fill this table out for you. If you want to pause the video and put this in your calculator and see the table for yourself, you can. But in the interest of time, I'm going to go ahead and just fill it in for you. Okay, so when I go ahead and I have the limit as x goes to 0 of sine x over x, I end up with this. Okay, so clearly, graphically, if you think about it from a graphical approach, the limit then, the limit of as x goes to 0 of sine x over x is going to be 1, right? Because that's what our table tells us. As we approach 0 from the left or from the right, it's going to this undefined thing. But because these numbers are approaching 1, our limit is going to be 1. Now, there's a long proof that goes with that. For now, though, I just want you to memorize that basically, and that number, or excuse me, that variable can be anything. If you just have the sign of a variable over that variable, as that variable approaches 0, then that limit is always going to be 1. And so how does that help us when we're doing a problem like one of these? What that allows us to do is to manipulate this problem so that we can actually use this limit that's in part A. So let me show you what I mean. If I have the limit as x approaches 0 of sine of 5x over 4x, and I multiply that by 5 over 5. And the reason that I chose 5 over 5 is because this, let me change colors here. This rule says as long as the two things, the sign of something over that something, the limit as the something goes to 0 is going to give me 1. And so what I can do then is I can multiply by 5 over 5, which is going to allow me to sort of move things around a little bit. So I can rewrite this as sine of 5x over 5x times 5 over 4. So I literally just changed these two numbers, right? I had to multiply by 5 over 5 because that's 1, so I'm not changing the value of the whole fraction, okay? But moving that around now gives me this right here. And one of the properties we talked about previously was if you multiply the limit by some constant, it's just that limit times that constant. This limit is going to be 1, and I'm multiplying 1 by 5/4, which then gives me 5/4. Okay? So if I can get it into this form, then I can use this rule to evaluate different limits. So let's look at the next one. I've got the limit as x goes to 0 of sine x over 5x squared plus x. Well, if I were to just go ahead and factor the bottom, in this case I don't need to multiply by anything. I can factor an x out of the bottom. Whoops, 5x plus 1. So that gives me the limit as x goes to 0 of sine x over x times 1 over 5x plus 1. And because this has an x in it, right, this is the limit of the product, so I just have to take the limit of each of these. So the limit of sine x over x is 1. And here I can do direct substitution. If I plug 0 in there, I get 1 over 1. And so my answer here is 1. Okay, so that is the first video. I have another video. The next video is going to finish out the notes for today, so we'll catch you in the next one.